Alright, so an excited hydrogen atom emits light with a wavelength of 397.2 nanometers to reach the energy level for which n equals 2. And we want to find what quantum level it began in. So there's two formulas that we want to remember and keep in mind for this problem. And one is that we know energy is equal to our constant of h times our frequency, which can be rewritten as c over wavelength, meaning that energy is equal to hc over wavelength. So the other formula that we need is E is equal to this constant times z squared over n squared. And in this case, we can write this as z squared over our n final minus z squared over n squared of our n initial. And in this case, we're going to be solving for this n initial. So now we can solve for our energy because we were given wavelength and use that for this left-hand side of the equation and solve for n. So we're going to first convert these 397.2 nanometers into meters. And once we do that, what do we get? So that's 397.2 divided by 10 to the 9th power. And we get 3.97 times 10 to the negative 7th power. And that's meters. And now we're saying that energy is going to be equal to our h constant, which is 6.626 times 10 to the negative 34 joules per seconds, joules times seconds, and we're multiplying this by the speed of light, so that's 3 times 10 to the 8th meters over seconds, and then we're dividing this by our wavelength in meters, which we just found was 3.97 times 10 to the negative 7th. So let's work this out. We do 6.626 times 10 to the negative 34th times 3 times 10 to the 8th, and then that divided by 3.97 times 10 to the negative 7th. And we should get 5 times 10 to the negative 19th, and that is our energy in joules. And now we're going to say, okay, our energy, this 5 times 10 to the negative 19th, is equal to negative 2.178 times 10 to the negative 18th times, and our z here is just going to be the hydrogen atomic number, which is roughly 1, so that's going to be 1 squared, which is just 1, over our n final squared, which we know our n final is 2, right? Minus, again, that atomic number 1 squared, which is just 1, over our n initial, which is what we're trying to solve for here. So I'm just going to write this as n with a subscript of I for initial squared. Keep in mind it's squared. And then an important thing to note is this energy was emitted. It wasn't absorbed, the energy that we solved for. So this is going to be a negative 5 times 10 to the negative 19th. And now we just need to use algebra and solve and isolate the ni squared. So let's first start out by doing this 5 times 10 to the negative 19th divided by our 2.178 times 10 to the negative 18th. And we get 0.2299 is equal to 1 over 4 minus 1 over this ni squared. So now I'm going to add to one side and subtract from the other so that I get a positive 1 over ni squared is equal to 1/4 minus that 0.2299. So that's going to be 0.25 minus 0.2299, which gives us 0.0201. And now we're going to multiply our ni squared by this. So we get 1 is equal to 0.0201 times ni squared. Now we're going to do 1 divided by that 0.0201, and we get roughly 49.9 0.75 is equal to Ni squared. We take our square root and we say that Ni is 7, approximately 7. And we're done.